Okay. Sometimes variable x and y is given as a function of a third variable. All right, so let's suppose I got x equals to 1 plus 3 cos b. All right, and I am told that y is equal to 2 sine b. Okay, so in this case here, that would be the third variable, and that would be my parameter. Okay, so that would be the parameter over there, which is b. So we want to find out if I have this and I, let's suppose, apply some kind of differentiation principles around an example related to this. Or let's suppose I'm given another question, that x is equal to t squared and y is equal to 5 minus 2t. And I want to find the derivative in terms of t. So I want to find the derivative in terms of t. So that means dy dx. All right, of t, keeping t with respect to t, you could say, with respect to t. Then to do this, firstly, in the first equation, I can find dx dt. And we know that's going to be 2t. That's straight from the first equation. From the second equation, I can find dy dt, and that's going to become negative 2. And so if I bring these two together and I'm find dy dx, then I've got to flip this one over, right, to make it dt dx, which is 1 over 2t, and then bring those two together and multiply it. Because dy dx multiplies dt dx multiplies dx dt, sorry, so let's double check that. Dy dt coming from here multiplies dt dx such that it cancels out, leaving me with dy dx. So if I multiply those two, then I'm done. Okay? So if I take negative 2 times 1 over 2t, it's going to cancel out, leaving me with negative 1 over t. And that would be the derivative in terms of t. So what is this? This is parametric differentiation. Why is it called parametric differentiation? Because I'm not deriving with respect to x and y anymore. I'm deriving with respect to t, and that's what I want to, at the end, find. All right, I'm going to find dy dx in terms of t. Okay. The second part of this, if I've got x equals t squared, and I've got y equals 5 minus 2t, and I found dy dx to be equal to negative 1 over t, the second part of this asks to find the equation of the tangent to the curve at the point where t equals 2, let's say. So if you want to find the equation of a tangent, the basics fundamental, whenever you see equation of a tangent, what do they actually imply? I want you to find y equals mx plus c. And they've just told you the m value. Y equals negative 1 over tx plus c. And they told you where t is equal to 2, so you know you can substitute 2 in there and get y equals negative 1 over 2x plus c. And now all you got to do is find the c value. So you got to substitute a point. So y equals negative a half x plus c means that you have to substitute some kind of x value and some kind of y value. Now, if I have the x value, let's say, if I've got x and y and I want to find a point that I can substitute in, let's suppose x is equal to 1. If x is equal to 1, then 1 will equal t squared. That means t will be 1. If t is 1, then y becomes 3. Right? If I make x equals to 1, then t becomes 1, and then that becomes 1, and y becomes 3, which means that according to that, x is 1, y is 3. So if that's the case, then I end up adding 3 plus half, which is 3.5, which is 7/2, which is equal to c from there. Right, that would be if I have a point that lies on it. If x is equal to 4, then t will become 2, and if I put 2 in there, y will become 1. Okay. And in that case, the tangent will be slightly different as well. But now, I can't just use any random point like 1 and 3, right? I have to use a specific point because it's a tangent. And because the tangent is intersecting at t is equal to 2, I have to make t equal to 2, which means x becomes 4, and if I put 2 in there, y becomes 1. That's the only value I can provide. So 4, 1, and I end up with -2 plus -1/2 times 4 plus c equals 1. And 4 divided by 2 is 2, so -2 plus, on the left-hand side, 1 plus 2 is 3, so c equals 3. And so therefore my final equation, y equals -1/2x plus 3. Like that. Okay, let's look at another example, right? The second example. Second example, what we have is the parametric. It's given that the parametric equation of a curve is x equals to 1 plus 2 sine squared theta, and y equals to 4 tan theta, and theta is greater than pi over 2 but less than 3 pi over 2. So that's 90 degrees, and 3 times 180 is 540 divided by 2 is 270 degrees. So we know that theta would lie in any of these quadrants over here. So it's basically from 90 to 270. Okay. All right. The first question says find dy dx in terms of theta. Okay. So I've got to derive each one. Okay. So I'm going to go dx d theta, which is going to be deriving that with respect to theta. That's going to become 0. The 2 is going to be brought out. And this can be rewritten as sine theta squared, like that. And from that now, I'm going to bring the 2 in front and multiply it by sine theta to the power of 1, right? Multiplying it by the derivative of the inside, which is going to be cos theta. So that's going to become 4 sine theta times cos theta. All right, so that's dx d theta. Let's move on to dy d theta now. Exactly the same thing. When you derive 10, it becomes sec squared. So that's going to become 4 sec squared theta. And I can rewrite it as 4 over cos squared theta as well. I need to multiply them to cancel it out, so I've got to flip this one over. So d theta over dx equals 1 divided by 4 sine theta times cos theta. And if I multiply these two together, dy over d theta times d theta over dx, I'll be left with dy dx, which is what I want to find. So that means I have to multiply those two together. And so therefore I got 4 over cos squared theta times 4 sine theta times cos theta over 1, and that becomes 16 sine theta over cos theta, which is 10. So it'll become 16 tan theta. All right, so just double checking that. That's going to be d theta over dx, which is actually, oh, I rewrote this incorrectly, right? So I've got to make sure I flip that over. Flip that over, actually 1 at the top, over 4 sine theta, so it doesn't actually cancel out so nicely. And that's going to get me 4 canceling out, 1 over sine theta times cos cubed theta, like that. Okay, that's going to be dy dx. The second question says, find the coordinates of the point. Now that I have that, it says, part B, find the coordinates of the point on the curve where the tangent is parallel to the y-axis. All right, so if we want to find the coordinates of the point on the curve where the tangent is parallel to the y-axis. So let's just have a look at this. So there's the y-axis, and we've got some kind of tangent which is parallel to the y-axis like that, with the curve on one side. We want to find the coordinates of the point on the curve where the tangent is parallel to the y-axis. Well, we know that the gradient is going to be infinite at that point. All right, the tangent gradient will be infinity, and it will be some kind of line, x equals something, right? Whatever value it is to find that coordinate there. So tangent parallel to the y-axis would mean that if I have to go back, this is my derivative or my gradient. My gradient is given by dy dx, and it's given by 1 over sine theta times cos cube theta. And in order for this to be infinite, we know we have to divide by 0. That implies infinity, right? The gradient would be infinite, which means that if the denominator is 0, then technically whatever theta value that makes it possible is the answer. So sine theta times cos cube theta has to equal 0. And so therefore sine theta equals 0 and cos cube theta equals 0. I could then cube root it. Cos theta equals 0. Sine theta equals 0. And now I can just solve each one. So theta is equal to shift sine of 0. And remember, my sine graph is 0 at pi and 360. So we know that theta can equal 0, pi, 2 pi. If I go shift cos of 0, it's going to be at pi over 2 and 3 pi over 4, 3/4 over pi. I think it's going to be 3 times 182 over 2, because it's going to be 270. So that's going to be pi over 2 and 3 pi over 2. All right. Now we did have limitations on this. Pi over 2 and 3 pi over 2 is my limitations, but it's not including it. So if that's the case, then we're saying that those two cannot be included. We do know that pi possibly would be the only one that's included in there. All right. So therefore, theta will equal to pi. And if theta is equal to pi, that means I can put pi into that. And we want to find the coordinates of the point on the curve where the tangent is parallel to the y-axis. So we want to find a coordinate. We want to find the x value and we want to find the y value. So if I know that theta must equal pi, then I know that I can go backwards and find it, right? Or I can go sine of theta equals 0. So therefore, sine of pi is equal to 1. And that's going to be my x value. All right. So that means that it would be the point 1 and 0 in this case over here. So going back to this equation, x equals 1 plus 2 sine squared. Okay, so going back, we're saying x equals 1 plus 2 sine squared theta. If I put pi in over there, sine of pi is 0, right? And so that is going to be 0. It means this is going to be 0. So x equals to 1. So what's left behind. So this equation is x is equal to 1. And so therefore, find the coordinates of the point, meaning that if it is parallel, it has to go through 0. So x equals 1 means that if I want to find the y value, I'm going to make that equal to x is equal to 1, just double check that. And we know that the y value will equal 0. And we know that if you have a tangent, y will be 0 when theta is also equal to 0. All right. So x is going to equal 1. So if I look at the second equation, if I change this into pi, what is tan of pi? Let's just go recap that. So we know this is pi over 2, negative pi over 2. And so every 180 degrees we repeat. So we know when my x value is equal to pi, my y value will be 0. So if I put pi into the second equation now, then that's going to get me my y value there. All right, so the first equation, x equals 1 plus 2 sine squared theta. Y equals to 4 tan theta. And so I substitute theta equals to pi in each case. Pi goes in there, pi goes in there. That will shoot out x equals 0, and that will shoot out y equals to 1, and that'll be my coordinate 0, 1. We normally do this with a single equation. We're now dealing with coordinates in 2 different equations every single time.